It just has like a bad rep for it and it's good. The edgy
Okay, so I'm trying to figure out what should the exam look like, and so there is this issue of, I think I told you a lot of things, but it's never really clear what actually got through. And also whether, since there are no pop quizzes, you might actually just be enjoying the sitcom or the stand-up comedy and going home. Obviously the exam would be an interesting way of figuring out what went through, but I thought, let me ask you, as we get started today, what do you remember from last class? A few things, something that caught your attention from last class. Yes?
the connection between A star and RL
Okay.
was something I was thinking about a lot after the class.
Okay. What does it mean?
Well, in my own work, we're doing some stuff related to RL, and somebody that I'm working with was thinking about it as search, and he was talking about it that way. So then, in one of our meetings, we were just kind of going over what we learned about, how your V values are mapping towards your heuristic, and specifically, we were focused on heuristic. So that's kind of what I was leaning into.
Okay. Other, somebody else? Yes?
Like me, just kind of the distinction between model-based and model-free, and what you need for each key values you don't need for model-based because model-free and just discrete continuous state spaces.
Anybody else? Yes?
In a way, since that you have this mapping between heuristics and the notion of what a value is in an MBT, you can actually even use LLMs to initialize your value, the states for a value, and then use that to begin learning.
So one interesting thing about MDP is that, it's actually worthwhile keeping in mind, I guess, is that you can, so one worry about A star search is needs admissible heuristics. Right? A star search needs admissible heuristics, which basically means if you think in terms of, remember the idea of A star search is think in terms of J star, which is the cast version of value, right? J star is the cast version of value. Essentially, you want to, if you are initializing, so A star search, basically, two things. First of all, I mentioned this, that one way of thinking about what A star search is doing is to compute the J star value for the start node. J star value for the start node. Can somebody explain to me what I mean by that? Not you. People who take notes are bad seeds because they probably know what's going on. So it's more fun to ask people who sleep during the class because that would be just, yes.
Does J star represent the, like, not necessarily correct, but guessed cost?
No, star part of it makes it optimal.
Oh,
So J versus J star. J star is optimal. J, no guarantee, nothing, no guarantees. It's just basically estimate. Right? So yeah, so what do I mean by saying A star search can be thought of as essentially computing J star for the start state. While MDP computes J star for all states. Right? That's the basic idea. When you solve an MDP to completion, you have computed J star for all states. A star computes J star for start state. Yes.
So, output of the A star algorithm is a whole path from which we can actually compute the actual cost, which is equal to J star. So, the cost to reach the goal can be computed. from the
Yeah.
start state.
So basically, you compute J star start node. I mean, the stuff that I guess we learned as really, really useful stuff, and again, is basically the connections between RL and MDPs and A star at one hand, and RL is basically sort of connected to MDPs where you're learning the model, right? So the interesting things that we mentioned, such as how you can go from value to policy, which is similar to going from basically the H star value to policy, right? Except you just need the path, right? So if I tell you the H star of all the nodes, so basically if you reach the goal and you tell you the H star of all those nodes, then basically you know which ones you're supposed to have gone to, okay? Okay. So that's about J star connection to A star. Any other comments about what people learn? Yes?
last time you mentioned if you know the whole model, then it's problem on the planning problem there was.
So if you know the model, it is a planning problem. But you can pretend it is a learning problem. This is like extremely important to understand a whole bunch of things that happens in AI. So it's a planning problem in sense. So by the way, there's this idea that one of the big names that you need to, I mean, I have mentioned it before, is deductive closure. Or similarly, inference versus learning. Deductive closure. So an inference problem is one where the model is given. It doesn't have to be MDPs. How many of you know Bayes networks? Probabilistic networks, right? If I give you the parameters of a Bayes network, right? So if I give you, so here is A, it basically, and then here is B, both of them affect C, which then affects D and E, and then I give you conditional probability tables for all of these. Okay? Then I've given the model of the network. Once I give the model of the network, if you at least learned my way, which is of my intro to AI way, I mean, obviously I believe that the only way to teach intro to AI is the way I teach it. So you should all definitely check it, if you actually like any of this stuff. So the way to think about it is basically with those CPTs, you get the joint distribution of the network on A, B, C, D, E. Once you have the joint distribution, any probabilistic query can be answered. It's just simple inference. You do marginalization, you do Bayes rule, you will be able to answer any probabilistic query. Right? So when people actually talk about inference in Bayes networks, you have the numbers and you basically the CPTs and you're computing the probabilities that are not directly represented there. The obvious probabilities that are represented here are you have represented P of A, you have represented P of B, you have represented P of C given AB, you have represented P of D given C, you have represented P of E given C. And if you didn't understand what I just said, you're in big trouble. You have to get intro to AI back to your head, or take it as some part of that. Okay, this is basically what you're giving. You're giving a bunch of conditional probabilities. And given those conditional probabilities, then in effect, you are representing the joint distribution. And once you represent the joint distribution, you answer any question. You can answer any question that's connected to those numbers. So inference basically means just crunching numbers normally. It's like, so one related name for this is deductive closure from a logic perspective. From logic perspective, right, if I tell you A implies B, B implies C, and D also is true, and B and D imply J, right? This is your knowledge base, right? The question is, do you need, so you can basically say this entails, right? This entails J. Right? That entails J. Entailment is an inference procedure. You see what I'm saying? Entailment is inference procedure. So when you are doing this, it's already in the entailment, it's already in the, given the knowledge this other knowledge just is deductively entailed. That's what's called deductive closure. Just because it's in your deductive closure doesn't mean that you directly recognize it. In fact, the computing deductive closure, even from propositional logic, is ONP hard. And computing deductive closure for first order logic, actually checking if something is present in the deductive closure for first order logic, which is entailed, is semi-decided. This can be very costly, but that's the inference part. Right? So you could have just crunched it end to end and you could have the numbers. There is no time you have to guess anything. Right? The other option basically is, so basically in the case of MDP is, if you know the model, it's an inference. If you know the model, it's an inference procedure. If you don't know the model, you need to learn the model. That's the inductive part, that's the learning part. Similarly, in the case of Bayes networks, if you know the CPTs, it's an inference procedure. Right? But if you do not know the CPTs, you need to learn the CPTs. In fact, one other thing that you may not know is you also don't know the topology of the network. I gave you the bunch of stuff was given in Bayes networks, right? In this Bayes network. I gave you the topology. The topology tells you how the joint distribution gets factorized. And then I told you the CPTs, conditional probability tables. with those two, you essentially get the joint distribution. And if you get the joint distribution, you can answer any question. You see what I'm saying? So that's basically that's the model part. So, but on the other hand, if you are learning the topology or learning those numbers, right? That's learning. How many of you know EM?
Are you referring to expectation maximization?
How many of you have heard of expectation maximization? Yeah. So EM, what does EM do? What it basically does is essentially, if basically, in the case of EM, what might happen, I'm kind of making a digression, but I want you to learn stuff, not just this course, so you might as well learn this. So if in fact, one of the things that, if you go back to the Bayes network lecture of 471, I explain that learning the numbers for the Bayes networks is extremely easy if you actually observe the full entries. That means you basically look at a world where A is true, B is true, C is false, D is false, E is false. Another world where A is false, B is true, C is false, D is true, E is false, etc. So these are called complete observations. So if I learn things of this kind, etc., right? Then if I give you a bunch of these kind of numbers, then computing those CPT tables is just taking ratios. This is what you do in Bayes classifier. You just take the ratios. Okay? The tricky part occurs if in some cases what happens is this may be hidden or latent variable. Used to use the charting. Latent variable means nobody tells you what its value is in the observed data. Do you understand what I'm saying? So what you will wind up finding is essentially, I'll give you the training data, learning the training data, which will be, I have no idea. And the other stuff is known. The stuff that I can observe, I observe. The others, I can't observe. Because if it's latent, it's inside the network. You have no idea. It has some semantics in the network, but you have no idea what it is. You see what I'm saying? So you basically have this kind of a data, and this is what is called the incomplete data. Incomplete data. When you give an incomplete data, when you are trying to compute these numbers, that's the learning part. It's no longer as simple as just taking ratios. Because in effect, you have to marginalize the unobserved variable C. Right? Again, look up I'm sort of pleading with you, if you don't know this stuff, watch the 471 lecture, so that by this time, after this class, you will be equal to that. So one thing that basically people tend to do is this expectation maximization algorithm, where it's a kind of actually a gradient ascent algorithm. What they basically do is they will guess values in the beginning for C. So the guess values for the CPT numbers in C. Right? And then given the values that are guessed, then you do the inference. That is the expectation part. Inference is the expectation part. And then after doing the inference, the next time based on the inference, you update the values of these CPT tables. So that's basically, you repeat this expectation maximization. That is combining learning and inference together. So the reason I brought up EM is, while it is nice to think of learning and inference are two very different things, which is they are true, you can combine them, you can interleave them, right? And the interleaving basically is something that people get confused very easily. right? So one of the issues is you could have this case, in the case here, you have a model that's fully known. But you may want to do RL on it. Because if you know the model fully, normally you are supposed to use planning and MDP techniques. But one way of not taking the information basically is act as if the fully known model is still not actually directly accessible to you. So it's like I give you like a big book and ask you to study everything you need. In fact, everything I can possibly ask in the exam is in all the lectures that I've given. But who the heck cares? There's too many things, right? And so the interesting question would be, you might try to, when given, let's say, something like a homework problem or something, you will try to wing it. And then, as needed basis, go into the notes to figure out what is needed. I mean, those of you who are still getting traffic tickets know that's the way we are supposed to take traffic exams, right? Nobody actually studies first and then answers. You have two windows. I'm not saying you should do it. I'm going to do windows. In fact, this was a couple of years back. Maybe now you just ask Claude to take it for you and you've done the same. But in general, just before Claude, you have two windows. There's a question, you control S that question in this document. It will tell you what the answer is. You pick it. Right? But exam is supposed to be inference process. You have already learned all the information. I'm just trying to check whether you can regurgitate it. But you're saying, during the exam I learned, quote unquote. Right? That can happen if you have the model, but you still apply RL techniques to solve the model. Because remember, RL ultimately directly goes, if you remember the picture, RL can go from experience directly to policy. And BP also wants to go to policy, but already has the model. So you can actually use all the RL techniques, and that basically makes RL a very lazy way to deal with, a lazy as needed way to deal with the learning part. So just like rather than study the traffic exam book first and then take the traffic exam, which is what they're expecting you should do, there's a learning phase, there's an inference phase, you combine them. You look at what questions come and then see what are the ones, where are the answers for those. Especially in open book exams, is exactly what you do, even in the exam, in the class, right? So the point that I'm trying to get at is, even if you have the model, you may very well close your eyes, not look at the entire model, do TD learning and basically get the pieces that are needed as and when they are needed. You see what I'm saying? So this makes it extremely hard for people to differentiate between RL without learning. So RL, which is actually being done because you don't know the model, so you have to learn the model, versus RL that's being done because you know the model, but the model is too big, and so you just want to kind of wing it as needed. You will look into the model. Do you understand what I'm saying? I would argue that many of the cases that you think are RL applications right now, everybody and their brother who calls it RL, because calling it RL is more sexy, as I told you, than calling it inference or search, okay, is exactly this. You can take a paper and then say, what is it that they don't know? What part of the model don't they know? You can't say, well, they need to know the policy, but not knowing the policy and quote unquote learning the policy is like saying, I don't know what 4 plus 3 is and I learned it. That's a silly way of defining learning. Do you understand what I'm saying? So essentially, even if you know the model, you might actually pretend it's a learning problem. Because that way, it turns out the important thing about RL is it's a weak method. Because it's a weak method, those methodologies can be applied in many cases. And it sometimes, when you can't actually figure out the details of how to do the policy and value iteration correctly with continuous dynamics, etc., right? You might just go out. And there's no learning there. You're just basically trying to remember the traffic exam. Doing traffic exam to get out of points by having two windows. It looks as if you're learning during the exam. That's because you chose not to learn before the exam. In pure RL, you cannot actually learn before. Without actually executing in the world, you don't know what is the state space. Here it was a choice. For pure RL, it's not a choice. Exploration is not a choice for RL. So in fact, one way you can tell that many people are using RL this way many RL methods are inference methods. Basically, they're just doing as inference. And one way you can tell, ask where are they doing exploration? Where is the exploration? If there is no exploration, right, then obviously there's no learning required. Essentially, the entire model is there. You're looking into the model as and when you need it. Do you understand what I'm saying? It's a subtle difference, but it's a very important difference because you have the model. In essence, the problems of non-ergodic worlds don't bother you, right? If you have the model, then everything is with respect to this model. So in fact, this is part of the reason why RL with simulator is planning. Planning basically means inference for sequential decision making. Because simulator is a model. And they don't fall from sky. Somebody wrote it. You have the simulator in front of you. And so if in fact simulator says you are dead, you are not actually dead. It's pretend dead. Right? That's how you do so well in Grand Theft Auto. Because when you die, you get up and go again. It doesn't happen on the rural road. And that real RL is rural road. You see what I'm saying? So that's the important thing to keep in mind about having the model and basically looking at in a lazy way. That's what I was saying. RL is a lazy way of doing planning in some cases. Okay? Okay, anything else? People? Yeah.
So could you explain one more time again?
What?
If you have the RL with the simulator, and you're saying that it is indeed planning,
Yeah.
but my confusion is coming partly from this part, that the agent that is doing RL doesn't have access to the simulator's rules. It just has access.
It has query access to the simulator. So the difference, that's basically, let me show you, since you asked for that, since I know, let me show you the specific case that will put that in perspective. Oh, sorry. Where am I? You see, as again, I have a lot of things to cover, but will I cover it is anybody's guess. This is already a third episode of RL and planning, but we'll see. Hopefully this is the last one. This example is worth doing because this is actually hitting two birds with one stone. because most of you don't actually know the difference between SAT and CSP. But I'll explain to you SAT and CSP, and then explain to you, RL with simulator and versus RL with declarative models. Okay, so the idea is, so this is basically what this is actually a repeat. And many of the things I'm saying have already been treated once. So good way to understand PDL planning versus simulator-based RL. By the way, you can do simulator-based planning. Right? There are many planning algorithms where if you just have a simulator and you say, can I do this action to the simulator? And if I do the action, what would be the next state to the simulator? And it answers those questions, it's enough. Those are called black box models. Simulators are black box models. You have only a query access to them. Inside is some arbitrary code, but it does things right. You ask it, it will answer. The advantage of PDDL is you have a representation of everything that's happening in the simulator, because you have the actions, you have the preconditions, you have the effects. You don't need to ask some random guy, can I do this action? I can look at this action, look at the precondition, and see if it is present in the state. One of the advantage of simulator, by the way, is you, the guy who is doing it, doesn't need to understand the state representation. You just need to pass the state representation to the simulator, which needs to understand it. You see what I'm saying? And if the simulator understands state representation, it says, yeah, you can do A1 this, and you get this state representation, and it draws like a new state, in the symbolic state or a picture state. That's a simulator. But you have the entire model. You didn't do it in the world. There's a piece of program, so there is no actual death. It's pretended. Do you see what I'm saying? So what would be the advantage then of using simulators versus declarative models? So the idea of simulators versus declarative models, there is a, it actually will come back again today. There is a distinction that old AI used to make between declarative versus procedural knowledge. And declarative is considered the gold standard. Logic is declarative, right? So you write everything in declarative form, then essentially your knowledge is accessible to you consciously. And so you can basically ask, it's not just a couple of questions, you can ask very specific. One of the advantages, because you have PDL model, you could talk about relaxing the model. For example, you can remove the delete effects of the action. You can remove the preconditions and see what happens. You could derive heuristics by taking the model in PDL specification and playing with the preconditions and effects. If I instead have a black box Bloxworld simulator, which takes the state and gives you a new state back, and it's correct, it's equivalent, and so with respect to it, you'll be able to do exactly the same correct planning that you can do with the declarative model. The thing you can't do is essentially, there are certain kinds of things. First of all, pure mental simulation is no longer possible. It all depends on what you mean by mental, right? So look at, this is the agent's mind. Obviously, agent's mind has been here, right? And then agent also has an access to simulator. And then out here is the big bad world. Right? The simulator is still, it's accessible to you, but it's not your brain. It's like calculator. You see, mental arithmetic, so the distinction between that is actually mental arithmetic versus calculator arithmetic. People who use calculator will get the correct answers. But they have no sense if it, in fact, they kind of mistype some number and it gives out the answer that is correct with respect to the mistyped number, they'll say, that's a number, they'll just copy it over. In fact, one of my colleagues long back, now this thing is gone too far, but 20, 30 years back, a colleague went to his kids' school and found that the way they were teaching them arithmetic is the teacher would write, let's say, what is 34 times 3, and he will say to the kids, now click 3, click 4, click X, click 3, click equal to, and then carefully write down what. That is simulator-based arithmetic. As long as the calculator is correct, you don't need to use this. You don't need to have a mental model of what you're doing. You understand what I'm saying? And in fact, by the way, this kind of stuff, as we externalize our brain, less and less of stuff we will do. I mean, I don't know whether it's a huge issue or not. I mean, it's okay to have the calculator do it, right? But this is basically, so then he pulled his kids out, because this guy was a kind of a Karmachian and didn't want the kids to kind of carefully draw the numbers in a pixel form. Remember, I was talking about one of the other things I was hoping some of you will remember is pixel arithmetic. Right? Right? Basically, you draw this shape, and then 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 you are supposed to draw this shape. Right? You don't have any symbolic notion. You can get it correct still. I mean, because as long as how many of you heard of Chinese room? Everything is connected to everything in life. You know what Chinese room puzzle is, right? Basically, for those of you who don't know, this is one of these kind of paradoxes, pattern codes, you know. There's a room, and there is like an infinite 2 storage shelves, and there is a window called English window, there is a window called Chinese window. And there is a, you know, maybe somebody who doesn't neither know Chinese nor English, just put like, you know, somebody, some Eskimo is in the middle, right? Who basically has a different language, completely don't understand Chinese or English. And what they do is they mechanically follow these things. When somebody gives them like, you know, like basically some number of English tokens, then they will take these. In the other thing, there are corresponding Chinese tokens. They remove them, and then they give it outside. And as to why they are the corresponding Chinese tokens, there's a lookup table saying this token corresponds to this. And the outside are Chinese people. Here on this side are the English people, and they are now able to communicate. The question is, does the guy inside the room understand? The interesting thing is, the guy inside the room neither understands Chinese nor English. Right? He doesn't understand, he or she doesn't understand either Chinese or English. And this shelf doesn't understand Chinese, it only has English tokens. This shelf doesn't understand English, it only has Chinese tokens. So the philosophical conundrum is, where is the semantics coming from? And you know, there are ways of getting out of this. One of the ways is, for example, that it's true that no piece actually understands, but the entire thing understands what it is. Chinese room understands how to convert English into Chinese. The guy in the Chinese room is just a cog in the wheel. That's one way of dealing, you know, with this. So, how did I get into Chinese room here? What was I talking about just before Chinese room? What? Pixel, yeah. So the idea is that you may be doing pixel or arithmetic, you actually overfit yourself to write. You learned a huge, you know, neural network, big neural network that looks at a picture which looks like this and gives out a picture which looks like this. People who know arithmetic think you are smart. But you have no idea what numbers are. Right? Okay, so, you know, one of the interesting questions about Chinese room puzzle is the connections to LLMs. You know, the mind-blowing connections between Chinese room puzzle and LLMs. Right? But we won't get into that. You know, I'll let you think about it, we'll talk a little later. Okay, so the interesting question, of course, basically is that if you have simulators, these are black box access to, you, instead of doing mental simulation, you are doing simulation in this room. Basically, you have access to the external simulator. And so what comes out of here is still correct plan. Right? And the question, the answer to your question is RL with model. Basically, the model instead of PDL, so the RL agent instead of PDL, they will have a model here, the translation model here. And a simulator, this is the simulator, that's just the world simulator. So RL will just send a query saying, if I do this action in this state, what will happen? Now, what is the difference between having a black box simulator versus having mental model? It's almost similar to, what's the difference between not understanding arithmetic at all and only having calculator versus having arithmetic in your mind too, and maybe sometimes using calculator. You see what I'm saying? And a great way to put this in perspective is these two very simple problems, SAT and CSP. I think, did I talk about SAT and CSP in the class once? Okay, so you know that SAT problems are essentially Boolean CSP problems. That means SAT is, you can think of SAT as Boolean CSP. That is, CSP is a set of variables and with their domains, and then some constraint saying this and this variable cannot have this and this value at the same time. Right? And so you can, if you have any problem like that, you can always write that, you can model it either as a SAT problem, or you can model it as a CSP problem. In the case of CSP, one of the advantages is each constraint is just a piece of code. It can be an opaque piece of code. And then you tell this code, are you happy with my assignment, my current partial assignment? And if it doesn't like it, for whatever reason, maybe it says, oh, x cannot be this value and y is this value. It doesn't even realize, it just says, this is wrong. If it's wrong, then you can basically still do backtracking and everything. Right? In SAT, you have, even before, you don't have to ask, you can actually do the simplification yourself during the actual search. Right? Basically, each constraint in SAT is basically represented as a Boolean logic formula of the following type: P R, Q R, not W, or S. Okay? There's a bunch of constraints like this. And so if I basically tell you I'm currently considering, I'm currently considering not P, not Q, W, not S. Are you okay with it? You'll say no, but you can see that it's not okay. And because you have the model, SAT can essentially, so the same exact problems can be modeled as SAT or CSP problems. Like if you take something like graph coloring, you can model it as SAT or CSP. The difference is, in the case of CSP, it's almost like having simulators, because each constraint is a piece of code. Right? And in the case of SAT, each constraint is declaratively in front of you in this mode. Now, what is the downside? The upside of having the constraint in front of you is, if you have a bunch of constraints, you can actually combine the constraints before you even look at partial assignment. You can do things like unit resolution. You can start doing things like take the constraints and do resolution on them to simplify them. So you combine constraints to derive new constraints, even before actually, before doing the search. Do you see what I'm saying? You could do that, and that's sort of equivalent to doing with PDDL things like look-ahead heuristics. Right? Because our relaxation heuristics, where you take the model, you remove the deletes, and then you make a planning graph. Imagine doing a planning graph with the simulator. You still have to call huge number of times the simulator with these extra things saying ignore the deletes, but you can't talk about it to the simulator. Because simulator only tells you, these are the actions, and I'll tell you whether you can do them or not. And you are doctoring the model when you are generating these relaxed heuristics. You can't doctor the simulator unless you went inside the code of the simulator and changed it. You see what I'm saying? On the other hand, there is, as this gentleman will know, in fact, there's one other guy in the room, SAT, CSP, and what is called 0-1 integer programming. Zero-one integer programming is another formulation for representing the same set of problems that can be solved by SAT or CSP. It all matters as to which one you feel better. Zero-one integer programming basically comes from the linear programming side. And as we were talking last time, in the case of linear programming, you have a bunch of constraints. The constraints, instead of looking like these, they will look like this: P plus Q plus R greater than 0. And P, Q, R are all 0, 1, either 0 or 1. The real variables, and in the end, they have to be either 0 or 1. If you give this model directly, you can do what's called the linear programming relaxation of the integer program. Because normally what happens in the linear programming is essentially you have this polytope, and as I said, you go from corner to corner to corner to find the optimal corner. But the corners don't have to be integral. They can be non-integers. And you can't optimize, for example, the best way to run this plane is with 2.35 number of pilots and 4.73 number of stewardesses and 80.7 passengers. That's the optimum. But there are no fractional pilots, nor are there any fractional passengers. So you need to look at among the integer solutions, which is the best one. You see what I'm saying? So you can actually solve the same set of problems with integer programming formulation. And that is also kind of basically declarative. It's declarative from a different language. It writes things in this kind of arithmetic constraints. Logic writes in logic constraints. CSP says, to heck with all, we'll just put a big black box. You can write whatever the heck you want inside. It can be a Python program, a C program. It could be like a little system, a physical system that simulates the outside system. I don't care. That's why it's black box simulator. And you only have like query-based access. So the disadvantage for declarative cases, the advantage, of course, is you get to do mental arithmetic, etc. Mental, are the relaxed heuristics and look ahead heuristics and so on. The disadvantages is sometimes there can be an arbitrary constraint that cannot be easily represented as a satisfiability clause. Cannot be easily represented as an integer programming clause. But there always exists some arbitrary piece of code that represents it. So compactness actually becomes an interesting issue. In terms of writing, people modeling the problem can write the code faster than write the model. So one interesting question about this is if you are going to ask the LLM for the model, what kind of model are you going to ask? Are you going to ask PDL model? Are you going to ask, like, just give me a piece of code that simulates the actions? And all of a sudden you actually can ask that, right? Because LLMs can give you pieces of code as well as like actual formatted precondition effect models. And you can write papers, lots and lots of papers kind of distinguishing between these two, but the real reason, the real trade-offs are basically the trade-offs on this track. Right? Declarative essentially means you get to do mental processing. The agent has mental processing abilities. It can easily do relaxations of the models, etc. And then simulator essentially is like still separate from agent, but between the agent and the world. And in fact, you can actually have multiple layers of simulators. Once we are in this, we can have a bigger simulator. Another bigger simulator before world. So I will actually check if the plan is correct with a simple simulator, and then if it is correct, then I ask the second simulator, is it really, really correct? And then if not, then if it says fine, then I ask the third guy, now I'm really, really kind of sure, then I do it. Right? The way I'm describing these simulators probably already makes it clear to you that I'm using the simulator to kind of check my guesses. So in fact, LLM modulo, normally we talk about it as LLMs with verifiers. You can do it as LLMs with simulators. Right? And if somebody writes the simulator, you could basically do LLMs with simulators, that will still be LLM machine. You can also learn the model, either as a simulator or as some arbitrary, like pixel to pixel transformer, which is like a Japa kind of thing. We talk a little bit about it. That too can actually be still inside. It's a non-symbolic simulator. It will still have an API access saying, this is what I'm doing, do you think this can be done? And the internal stuff has no symbolic explanation, but outside comes the correct answer. That's a world model. That's a learned world model. You see what I'm saying? The PDDL models, these simulators and these PDDLs, we are just kind of acting as if the user domain writer gave it, but you could also learn them. And the idea of world model research is basically learning it, separate as a separate activity, and then use the model that's learned. The question then is, once you learn the model, how are you going to use it for? And the interesting thing is people leave it open. Jan, for example, is a big fan of world models, which is kind of funny because world models were there in AI forever. The question is, if you have world models, the normal thing to do would be the usual PDDL planning. But I could argue that in this day and age, you can actually do LLM module with the world model. And there are some advantages because these LLMs have been trained on all sorts of things, so they are actually pretty good guesses. All you need to check is whether it's correct or not, and the world model tells you whether it's correct or not. Or it gives you partial guarantees. Did that anyway answer your question?
Yep.
Okay. So that's the level of the distinction between simulator versus declarative knowledge versus knowing the model versus learning the model. These are all different axes. Yes.
So you're kind of continuing off of what he said. So you're saying that pure RL doesn't use simulators.
Pure RL uses Word.
Yes. So
Word
but
is
then-
not simulator.
But then that means that pure RL wouldn't be possible because once your agent dies, it's dead.
Yeah.
So you
But
can't-
the point is evolution made multiple peoples at the same time.
So then that's
I mean,
kind of
there was,
important.
it's like, obviously we have no idea, we were not there, but it's not like Lucy was the first, and then from Lucy, and then Lucy has to walk very carefully in case she dies because the entire humanity is dead. That's not the way it was happening. You understand what I'm saying? There are multiple people all the time. There were multiple people all the time, and they were learning from each other. You have to consider that possibility, because if it's only a single person, RL, what were they going to do? After they're dead, nothing. I mean, unless you believe in some sort of a, heaven or hell sort of nonsense. Right? So you're dead. And, other people learn. In fact, humanity's knowledge is completely based on other people's mistakes. Sometimes our mistakes, but we learn from everybody's mistakes and everybody's successes. And the cumulative effects of civilization just cannot be underestimated. Right? Over the weekend, we were in Montezuma Castle. How many of you have seen Montezuma Castle? It's on the way to Flagstaff. This is this Native American ruins. Lovely, lovely building. Okay, basically, I can show you the picture after that. And the first time I remember when I went there, I was like, wow, what a nice thing, what a nice thing. And my wife from behind says, do you realize that that's about the time Taj Mahal was built? Right? The difference is not Native Americans versus folks in India. It is the cumulative effect, the accelerating effect of civilization. An itinerant civilization basically it has to start from scratch every once in a while. There's only so much, especially when you have oral knowledge alone, then there's only so much that can be passed along. You see what I'm saying? Settled civilization is why we are here. Settled civilization depended on written knowledge. And to say that we can, we don't need language, we can just somehow get from pixels to where we are because we did get here, seems kind of silly because it takes forever to get here. There was a question. Yeah.
So are you saying that the only real RL, or the only pure RL in some sense is null pointer?
All I'm saying is that pure RL in an ergodic world can be still an RL. In fact, one of the things, again, what I'm asking you is, I am actually wondering, if I had another semester to continue, then I would have said things like, pick a paper and show what are they pushing under the mat. That's what you read papers for. Not about, they already hype their paper. Why the heck are you hyping their paper? Your point is to figure out what did every paper has pushed something under the mat. Otherwise the science is over. Right? There are very, very few times where a particular area is closed and nobody comes back. You want to understand what are they pushing under the rug, under the mat. Do you see what I'm saying? So the interesting question is, in many, many, many cases where they have a single agent and an RL, it either has to be either has to be an ergodic environment. That means actions won't get you into states from which you can't come out. There are such worlds, especially like if you only do reads on the internet, on the web, you can't get into trouble. Reads, just reads. That means, read and write, they're the two things that you can do on the web. If you're only reading, it's an ergodic world. Not surprisingly, quote unquote, large number of agentic applications are read-only. Right? And so they can't possibly get stuck in things, or they can't possibly make the agent get stuck in a state from which they can't come out. Once in a while, they'll throw in a write action, such as delete files. Delete files is writing action because it's changing the, and then they hope for the best that whenever you have non-ergodic world, planning becomes important. The fact that it seemed to work last time doesn't necessarily mean that it's always going to work. The issue is it actually guaranteed? And if it's not guaranteed, once in a while it will die. Once in a while, like your mails will be deleted. So if it is a single agent RL that seems to be hanging around without any problem, it's probably because it wasn't even doing RL, because there's no learning going on. It was actually a full model and it's just using lazy RL. It could be a world that is ergodic. Do you see what I'm saying? Or it's not actually working on the world, it's working on a simulator, which again means that basically it's not learning to begin with. Simulate-based RL is an oxymoron. And this is why nobody calls me to RL conferences. Because they all believe that simulator-based RL is a thing. It's a thing in a very different way. It's basically the lazy approach. So by the way, I should tell you, these distinctions are very nuanced. So, if you're trying to compute the probabilities here, right? I showed you that in the case of just inference, like EM essentially, to even do inference correctly, you need to learn the numbers because the intermediate node numbers are not known. And then you need to do EM, so that sort of effectively combines learning and inference. There are other methods that you have heard of called variational methods. What's a variational method? There is an arbitrary distribution. Doing inference on that distribution, even though it's just inference, doing inference on that distribution is too costly. It's intractable. Intractable is the word people use in probability because that means it's exponential. Right? It's costly. So what do? You try to find another distribution that is sort of empirically close to this distribution. And it has all nice properties, such as exactly tractable. So take a tractable class of distributions that is closest to the distribution that you're trying to approximate, and then basically find it. And so you finding it would be calculus of variations, because you essentially have to find the best tractable distribution form which is closest to this unknown distribution, which is intractable. And you heard words like KL divergence. KL divergence is nothing but a distance between two distributions. KL divergence happens to be asymmetric. Shannon, Jensen, Shannon happens to be symmetric version of KL divergence. So you write a loss function to look for an inference, a model that is close to the model that you are actually trying to do inference on. And so first you learn this tractable model, then you use it. So to do inference, you first find an approximation, which is learning part, and then use it. Do you see what I'm saying? So it is true that one is inference, one is learning, but sometimes for various computational reasons you'll wind up doing this. You have to remember why you're doing it. That's important. You see, the deeper part is sometimes you cannot do it without learning. But when you're doing variation inference, it's just for efficiency. It's not really because the knowledge is not available. Do you understand what I'm saying? So in general, deductive, there's a difference between, is the learning kind of trying to increase your knowledge? Or is it just trying to make clear something that is already present as an entailment of what you know? And the second is called deductive inference or deductive closure. And the first is called inductive. And you wind up doing, sometimes you do one part inductive and then do deduction on that. That's exactly what happened in the variation inference. Yeah.
Was that directive versus deductive?
What?
Or what were the two types?
Deductive versus inductive.
Oh, thank you.
I mean, deductive has a closure. Inductive doesn't have a closure. Inductive, you can make up stuff. There's no closure. Deductive essentially basically says, for propositional logic databases, for example, the deductive closure of the propositional logic database is a finite set database. For first order logic, that's not true. Because of this ugly thing called functions. And very easy to get about it. Okay. Anyway, anything else that anybody wanted to bring up from next class? Okay, good. Yeah, like I said, I started with this, and I always have this problem because it depends to some extent on how much are we saying versus how much people are getting. I mean, this is not meant to be insulting. Please understand that. Although there's a dog and there's a human, and we talk in big full sentences to the dog, and what does the dog hear? And the question, of course, is when teachers are teaching, the question is what is it that other people are getting? And there are two ways of understanding this Far Side cartoon. One is, the dog is stupid, right? Which is what you would think, and you will write bad comments about Rao saying he's equating me to dogs. But actually, an equivalent version is the human is stupid. Because the human basically doesn't have a mental model of where the dog's knowledge state is. And randomly talking about things that other people don't understand is not working either. I mean, I do a lot of gesticulation, etc., and I look at people's faces to see how well they're asleep. But you cannot be completely sure that anywhere above 20% transmission is going on. At 25%, it's a great class, honestly. But if you get something above 50%, you learn stuff that took me forever to learn. That's pretty much the point of doing teaching. Because if you can read up and get to where I am, then why am I here? Right, essentially, right? So anyway, a couple of these things. This one, was with a sufficiently pixelated input, any AI problem can be made to have polynomial input complexity. By the way, there is a whole set of things called AI aphorisms. If Twitter is working well, if you hit on AI aphorisms tag, you'll get all of these. And there's a statement about Reduced Shakespeare Company. Has anybody heard of Reduced Shakespeare Company, which is basically a parody of Shakespeare? And the tagline is, the better you know the original, the funnier the Reduced Shakespeare Company gets. Parodies are not interesting if you don't know the original, right? Because you don't know what they parody, right? And you will enjoy the AI aphorisms if you understand AI. Because I'm basically catching the things that I assume people basically get it from. So one issue is, this is what I was telling you last time, with sufficiently pixelated input, any AI problem can be made to have polynomial time input complexity, which is basically like why MDPs are polynomial while PDL planning is piecewise computation. Because the input specification of PDL is logarithmic in the input specification of MDP. And in general, the whole point of symbolic anything, abstraction anything, is it humongously compacts the stuff that you have to transfer. You see what I'm saying? And so, in fact, in some sense, in this compacted input space, the complexity will be higher. But that's still winning. Right? And also, generalization is much more interesting if you are doing it in the compacted space rather than in the pixel space. Right? Because what am I supposed to do? If I think of 7 as just this, right? What are the generalizations I can do to 7? Right? If I put a couple more pixels here, does that keep it still 7? Is it an interesting kind of a 7? Is it 7's girlfriend, boyfriend? We have no idea. It's just another picture, because the advantage of pixels is there can be a pixel for 7. They can be like there can be a picture for 7. There can be a picture for your pet cat. Both in the same place. PDL can only represent one of them, like a calculator can only represent one of them, not the other. Do you understand? Representational bias basically ultimately kind of reduces the things that you can represent. But it also takes you higher. Okay? Anyway, so keep that. So generally, if you blow up the input, you can always reduce the complexity. And that's a dumb way of reducing the complexity. But your reviewers may not know. So I'm both telling you how good AI is supposed to be and also how to get many papers. Because you can assume that most of your reviewers haven't taken this class. So, yeah. So this one I was actually, I don't know why you put this, but so remember, there's an ICLAIR paper this year, 2026, whose abstract, it was on about RL for LLMs or something, and it ends this. And so you can tell your mom that you're doing LLM level planning, right? Because finally, applying your framework to the real world planning benchmark Bloxworld. Real world planning benchmark Bloxworld. So we made Bloxworld great again. Right? It all depends on what people forget. If they forget, then you bring it up, then it suddenly becomes, there are different ways in which planning problems can be hard. And Bloxworld, and even more importantly than Bloxworld, the Sokoban. Sokoban is the one which is Sokoban you should remember as the one simple toy problem that is non-algorithmic. Because Sokoban is this problem where you push the boxes, you can only push them, you can't pull them. Because of which you can't reverse the actions. When you can't reverse the actions, that's a simple way of making it world non-algorithmic. Because you can get it straight and not come out. So you have to plan beforehand. And by the way, all the numbers for Sokoban, for planning, for most of these guys, is extremely worse compared to the numbers for law. Right? It should not be surprising. So you should know how to make things do bad, as against be impressed that they're doing well. That's the whole point of being scientists. Right? Okay. Then this one. Okay, so I am using RL on semi-DEC POMDP with a single agent facing goals of achievement in a fully observable environment using known instantaneous action models with deterministic dynamics. What am I saying? I'm saying that please give me the best paper award in ULIPS. But what am I really saying?
I'm doing some sort of reinforcement learning.
No.
It's contradicting.
What? Why is it contradictory?
It's fully observable environment, but it's POM-DP.
Yeah, but no, it doesn't contradict. POM-DP is partially observable. Partially observable one type of it is fully observable. How many of you think RL is only for stochastic domains before you came to this class? You thought so, because MDPs are stochastic by definition. How many of the LLM papers that supposedly use RL actually use stochastic domains? They are using mostly deterministic domains. In some sense, you can argue that I'm cynically back in LLMs because real planning is hard. If I go to IT Labs, I have to start doing actual, I don't know why you guys are doing it. You have to actually do stochastic planning, with harder and harder, plan lengths, etc. Here, I get to basically keep making fun of these guys because they can't even do, blocks work. Right? So nobody said that, basically, so what am I saying? I use RL on semi-deck POM-DP with a single agent facing goals of achievement in a fully observable environment using known instantaneous action models with deterministic dynamics. What actually am I doing? What?
Ref search.
Yes, star search. Yes. So don't say you're doing A-star search because then people will kill your papers. A-star search, old stuff. Similarly, if you say I'm doing planning, it's old stuff. RL, very good. So if you know your reviewers, you can manipulate it. You can game the heck out of it. They're stupid, so you will use them, essentially. And that way they have to learn something. This is what I'm saying. Because many of the papers that are getting in basically are because the reviewers don't know what's going on. This is not happening in quantum mechanics. Because nobody enters quantum mechanics. But everybody enters AI. Everybody is writing papers in AI. And there are not that many people who know anything. Just be cynical. It's reasonable to assume that there are not that many people who know everything about anything. And so, like business school has an AI major right now. That's supposed to be. Honestly, my cousin's son, I just met them because he came to AI. The business school orientation this morning all the way in California. And they said, I'm doing the AI major. I said, yeah, I'm sorry, I'm an AI guy, but I guess these guys are doing it too. And the School of Computing is now worried that all the other people are doing AI. It's become meaningless to some extent. But that's because too much popularity. There's nothing wrong with the subject. And you need to understand, what parts are, how people are actually confused. That's the whole point. So, in fact, I had a tweet, I was trying to look for it, but today, for some reason, Twitter broke in terms of doing from user search, from raw to Z, but so I kind of recreated this. But this is a good thing. Basically, variations of this are used everywhere, RL, when the model is known, and it should be called planning. Right? And the reason why I'm saying I should be called planning is not because I care about names, because I care about consequences. Because if you think there's some kind of learning going on, you have to think about the exploration and all this stuff. If you think it's just inference that's being done lazily, it's a different set of questions. What you call matters from that perspective. So anyway, that was, we were talking about planning and RL, and most of RL before recently has become this deep RL stuff, which complicates matters a lot more, but we talked about this last time, about atomic planning and how RL, and basically this stuff, and much of this discussion should kind of make it clear where RL versus planning. Correct? The model base versus model free is just one axis. The simulator versus declarative model is another big axis. And planning is all about, in general, ICAPS, and so the PDL style planning sort of a thing has been all about knowledge based. So you give the knowledge of the actions, you give the knowledge of the task reduction schema, you give the knowledge of your preferences, you give the knowledge of your goals. You see what I'm saying? And so those are basically required declarative models typically. Right? And so understanding that is actually, very useful. Basically, the PDL model is a world model. It's a type of world model. Simulator is a world model. It's another type of world model. Pixel transformation is a world model too. That's another type of world model. Ultimately, in the end, world model gives you at the atomic level transition function. What's the probability that you will be in state as dash, given that you need action A in state S? And these are all different ways of representing. And PDL, etc., are very compact ways of representing. Right? Then the other thing about RL is rewards are basically this assembly language. In some sense, people may not actually provide rewards. They will give you, especially if you have people in the loop, they're likely to say, get me this goal while these constraints are being satisfied. Then, if you want to use it as an RL reward metric, you need to compile it into a reward function that is consistent with the high-level goals that people have given. Now, turns out that that's not a simple thing to do. It is true that reward function, once you get the reward function, you can get the MDP process going, whether it's RL or MDP. Right? But if somebody else basically has a particular set of goals and with some constraints that they want the behaviors to satisfy, right? They are likely to give you these constraints in symbolic form. Or give you sometimes, you show them two behaviors, they say, I like this, not this. So they either give you like this sort of, I like this behavior more than this behavior. Or they can actually give I would like you to reach the goal in the fewest number of steps with none of the steps essentially ever violating this condition. Both of them are reward functions. And both of them are like high-level reward specifications. You have to convert into reward, right? And converting into reward is not as simple. One of the weirdo things that happens typically is even if the MDP is Markov, because it's MDP, that means the transition depends only on the state you are in. The reward may still depend on the history. So you can have Markovian dynamics and non-Markovian rewards. If you have non-Markovian reward, you can compile it into a Markovian reward by blowing up the state space. Oftentimes, one example that might happen is, imagine the following kind of a problem. I don't know why I'm thinking about it. IMAX with 3D glasses, right? You went into an IMAX movie, and you're supposed to enjoy it, but it's all blurred. And the reason it's blurred, and Rob said that if there's a reward, you should be able to, the reward should wash over you, right? And it's not washing over you at all, it's all blurry. Well, it turns out that before you go into the movie theater, you're supposed to pick up these maybe questionably washed 3D glasses and put them on your face. Then the reward will wash over. Do you understand what I'm saying? So it's history dependent. If you went through the state where you picked up the glasses and then went to the state where you're sitting in the theater, then the reward will wash over. If not, the reward is washing, but you can't sense it. You understand what I'm saying? Right? So that is a classic example, one of the classic examples of non-Markovian reward. So the reward that you will feel in the theater depends on whether you did something before going into theater. Okay? So then you could, yes, go ahead.
But at that point, isn't the fact that whether you are wearing the glasses or not is part of the state?
It depends on whether it's part of the state or not, is my point. So the reason this might be the case is because you didn't model the state variable saying I am wearing glasses. That was an extra state variable. So it turns out that you can be in theater while wearing glasses. That's a different state from in theater without wearing glasses. That's a different state. You think in the theater, but they're two different, logically different states. If you never had a state variable called, having glasses modeled, then you can't actually say this. You will only have to actually talk about it indirectly as the state, history. So either you will actually, do the either you actually do the reward as a trajectory constraint. That basically you have to remember the history, and based on the history you'll get the reward. Or if you want it to be Markovian, you need to blow up the state space. You need to blow up the state space. That basically, blow up basically means you have to add this extra state variable. You do realize that if you add one Boolean state variable, you effectively increase the state space by how much? Doubled it. You see what I'm saying? You add an extra state variable, you doubled it. Okay, so that's basically what we are saying. You can compile non-Markovian dynamics or rewards into Markovian ones for equivalent MDP with a bigger state space. It can be either for rewards or dynamics. For the dynamics, I told you that TOM-DPs can be compiled into fully observable MDPs, but except in belief states. And similarly, for for rewards, oftentimes you can just introduce extra state variables that will essentially be able to let you model that reward without talking about the history. Okay. So this is another one more of these planning and RL terminologies, and a whole bunch of things that planning talks separately about are all just reward from the RL side, because it's just assembly language, right? I mean, think about the following thing. That's the whole point of high-level languages. In any high-level language, there is a for loop, there is a repeat until loop, there is some other kind of a loop, etc., etc. They're all different things. You go to the machine language, it's just the same. It's just go to statements. They're different at the higher level language, but they're the same mess at the assembly language. So the fact that everything is like basically numbers on the states, you could either think of it as a good thing or a bad thing. Right? The fact that reward is like just numbers on the states is like saying in the end code is all just like machine instructions with a go to state. But there's huge advantages to think in terms of high level code. You see what I'm saying? So keep that in mind. So goals are reward, trajectory constraints are reward, preferences are reward, and even heuristic is basically value, but you can also think of it as reward shaping. This idea of reward shaping essentially is you kind of add a specific extra amount of immediate reward to the goal. So the idea basically, when you put pink donuts on the way to the library, so that Homer will basically find a policy that takes him to the library, even though he hates libraries. You reward shaping. Right? And pink donuts don't naturally occur in the world. You put them there to actually, and at some point of time pink donuts will go away, and your hope is, supplying pink donuts forever is going to be very painful. You hope that this guy will eventually realize how beautiful the library life is, and then we'll start not caring about the reward. So this is actually what happens in reward shape. The real reward is you adding some extra stuff to the real reward. And the question, of course, is, are you still going to get the optimal policy? That would have found with respect to the non-trivial policy. That's the issue with the reward shape. Okay. Now let's get to the non-atomic story, which is kind of more interesting. Of course, I've been talking about it when I talked about declarative, etc. I'm talking about non-atomic story, not just atomic states. So in the case of non-atomic, things kind of diverge. AI planning generally focused on explicit knowledge tasks, which can be modeled as declarative models like VDL. RL tended to focus on more implicit knowledge tasks, where there is no declarative models. There are other kinds of models. They may not be logical models. Sometimes they can be differential equation models. Those are still models, right? Or they can be just simulators. And the problems are the same, but the way the word model is actually being taken as input is different. PDL, not everything that, like for example, you're doing, many of you know inverted pendulum can be written as a MDP problem, right? Right. So inverted pendulum is a pendulum is standing like this, and it's on a like a smooth cart, and you have to keep moving the cart such that the pendulum stands. Right. It's a control problem, really. And so you can write that essentially as an RL problem. But imagine writing inverted pendulum model as a PDL model. It would be very awkward. In general, when you go to higher level languages, the higher level languages are good at certain things and bad at certain other things. Everything is equally bad or good at assembly language. You see what I'm saying? From the point of view of assembly language, we haven't changed since like 1940s. New technologies come, there is multi-threading, there's this, there's that. In the end, it's just assembly language. You make this religious wars about is it C versus Python or C++ versus Rust versus something else, but it's all in the end, it's an assembly language. And so everything is actually representable in assembly language. But that's not necessarily a positive thing. Because sometimes it's easier to write things in these higher level languages. It's easier to, and even for LLMs, because it's easier to write things in higher level language, there's a lot more higher level language programs that are part of the LLM training data than there are assembly languages. Because that's what we've been writing mostly. Okay, so that's the important thing to understand, that planning focused on explicit knowledge tasks. And the idea of explicit knowledge tasks is declarative models, basically. Implicit knowledge is you call, okay, and then it just gives you, is the action done, and if so, what is the new state? And that's how the world works. That's how simulator can work. Simulator is the world standard. The PDL model can be more than the world itself, because it also allows you to do mental arithmetic, mental model. Okay. So in the case of explicit knowledge tasks, the RL systems can either use partial models representations supplied by the humans or learn their own representations from raw sensory data. And this is where things become questionable. If in fact the models are easily available from the human data in a higher level, who are you trying to impress by trying to learn the same model from pixels? And as I mentioned in last class, Atari games is a classic point. If you are doing Atari games benchmark right now, you would not do it the way DeepMind did it. It makes no sense. Right? Because you don't see pixels when you see Atari games, you the human. You think in terms of symbolic concepts. They didn't know how to make the system, basically, they didn't like people to give the symbolic concepts to the machine. So they basically said, start from the lowest common denominator, which is pixels. But that's unnecessary in the era of LLMs, because actually you don't have to ask anybody. It's already available from GPT-5, because GPT-5 asks everybody. asking one single person is bad. Asking the entire humanity, or just co-opting the entire humanity is good. Right? I mean, this is what basically they say, that if you lose money as yourself, then that's like a small bankruptcy. If JP Morgan sort of loses all the money of the country, then that's like a country's problem, not their problem. It's a very different kind of, things. So anyway, so for the explicit knowledge task, RL actually, I would argue that in the old days, they would still try to do explicit knowledge tasks in the tacit representation, because you can do assembly language programs. If you can do things that can be done in higher level language in assembly language, because everything can be done in assembly language. But if it can be done in higher level language, you should actually do it that way because it's faster. And in the past, they would not do it because you have to ask somebody. But now LLMs will give you this higher level knowledge. You show them, the same with the VLMs, etc., multimodal things, and they'll actually look at the picture and they'll actually recognize objects and they'll basically give you some sort of relational description. It doesn't have to be in the exact language syntax. You're on a much higher level than thinking in terms of pixels and, like salient, series, G, and etc. Okay? For tacit knowledge tasks, they have to learn their own representations. This is understandable. So if in fact, that's why I said, like, there are things like, the tricky part is there are obviously many physical manipulation tasks, etc., where, like, how do you pick up this thing, normally just pick it up. But then you can't tell the robot, just pick it up, and it has to do this or something, and pick it up, etc. And, we don't have good symbolic ways of representing this stuff. So you might as well let it learn just by looking at our representations. Do you understand what I'm saying? So that makes sense to do basically deep RL, JAPA style sort of models would make sense for this, but not for this. And you have to ask yourself, who are you? First of all, civilization would have been here if in fact most of our problems are only tacit knowledge tasks. There's a huge amount of explicit knowledge tasks that we do. That's why we have models, we have books, etc., etc. And everything that is explicit knowledge task has become training data for LLMs. The weird way in which the circle turned, the wheel turned, right? It was like we should ask anybody to, everything that people know is available free, more or less, at some level of abstraction. The only thing that people then put on the web is how do I pick up stuff, because everybody assumed that's not what I'm talking about. And they didn't know how to say how to pick up stuff. It is interesting, weirdly enough, we are such language animals, such linguistic animals, that we still try to provide language descriptions for stuff for which there is no real use of language. I mean, what the heck is food critics? How many pages can you write about how pizza tastes? Just beat the damn thing. That's pretty much the only way. Writing 3 pages, who gets happiness out of it? I guess some people do, essentially, but I don't know what sort of they are. But the point is, things like paste, etc., you can write a lot of stuff. And we write mostly because we are such linguistic animals that even things that are truly, essentially, essentially the tacit knowledge tasks, we still give partial explicit knowledge descriptions. We'll give names to the case. We'll give interesting kind of names to talk about textures, etc. But it will always be partial, essentially. Which is why actually when they do, so one of the interesting questions in these sort of things is even in the fully tacit knowledge task, people might have preferences, and the assembly language for giving your preferences to the machine is by being shown this versus this, what do you like? Do you understand what I'm saying? This is basically, I mean, how many of you, okay, all the people who have glasses obviously know this, right? That they don't basically, there is no quick way of telling what power glasses are right for you. Instead, they make you sit there and say, this versus this, which one do you like? This versus this other one, which one do you like? After a while, I'll say, no, 18 times back, that one was better. I don't know, it's like very hard to, but the point is, there is no way they are trying to get your preference by making you do pairwise comparisons. Pairwise comparisons is the assembly language of preference elicitation. Write that down. There's this guy called Paul Cristiano, who became very famous for essentially saying that if you have a bunch of pairwise preference data, like people say, I like this better than this, for anything, like, and in particular, if it has pictures, it's very simple. I like this picture better than this picture, right? Then you can convert those pairwise comparisons into a consistent reward function, and then run RL or RLM deep learning. Again, as I say, most people when they say run RL, they actually might be saying RL with complete mod. Okay, but pairwise comparisons are actually, the only time you will do pairwise comparisons is if there is no other way people can tell you what they like. Civilization would be really, really slow if you have to give information about what you like by being shown two different things that which one you like. We develop lots and lots of abstract concepts to talk about what kinds of things we like. Now again, the assembly language metaphor is extremely important. Anything that can be done in the higher level language can be done also in the assembly language. But assembly language, either writing or eliciting, is very costly. You would only do it if people don't know how to explain it all. Those are basic concepts. So for example, what kind of walk is graceful? What kind of food is tasty? I can write a bunch of pages, there are dance critics, there's food critics, but they're all bogus. Right? Essentially, there are some egregiously bad walks and egregiously bad food, but all sorts of interesting things. We don't know how to express what we actually like. In fact, as you know, there are things that other cultures eat that you basically thumb your nose at, and vice versa. Right? Pretty much everything that you think, I would never eat, somebody else eats it without any problem. And for them, they'll think, oh my God, you eat pizza? Very bad. It's all depending on what you've grown up with, that's it. You understand what I'm saying? So in those cases, pairwise comparisons is fine. If you really, really didn't know any other vocabulary. But if there is any better ways of providing preferences, such as in language, you take it. And all of a sudden, pairwise preferences go out the window. So pairwise preference-based preference learning is only alive and well in like a couple of places. One is this sort of, what is a graceful way of walking versus not graceful way of walking. And you don't know how to define it, you just give a bunch of examples and say which one. And you get these pairwise comparisons and you try to learn a reward function that approximately is actually kind of consistent with those preferences. And it turns out, actually, one of the dirty secrets, and I have a tweet about it somewhere, is graceful walk. Oh my God. Okay. Oh, so in the beginning of the semester, I thought I was in the middle of the class, I was talking so much that I was having like vertigo. And I actually thought, something was going on, and it turns out this thing moves very smoothly. So when I'm writing, it is moving, and I'm thinking that I'm having vertigo. But anyway, so what was I talking about? The gracious walk is non-Markovian, man. You understand this? Gracious walk is non-Markovian because it is independent. Right? I mean, if you nicely walk, couple of, and how many of you have seen Ministry of Silly Walks? Okay, you have to see it. This guy is definitely, many epsilons higher up the grades. Right? So, Ministry of Silly Walks you would see. So the point is, essentially, a walk being interesting or not interesting is actually history dependent. It's a trajectory constraint. All trajectory constraints by definition are non-Markovian rewards. Do people understand this? If it was actually, if you could write it as a state-based preference, you wouldn't have had to write it as a trajectory constraint. You see what I'm saying? Anyway, and one of the funny things is when people do these sort of gracious walk stuff with preference-based learning, they don't quite actually tell you how did they blow up the space. How did they introduce the history dependence? It's just that there's nobody else to compare it with. What are you going to do? I mean, I'm calling a lots of sacred cows by name, essentially. Like I do remember actually in 2017 is when Paul Cristiano was presenting this paper, and I was at New Rips, I think it was Long Beach or San Diego, and I asked, why is this interesting? Now obviously, what do I know? I mean, that obviously was interesting for a large number of people for various reasons, and so we have like a zillion citations. But you have to understand when is it useful. It is useful as the last resort. It's useful as the last resort. That even random things like who do you date is as tacit as it gets, right? Honestly. Like interestingly, one of the interesting things is civilization, as impressive as civilization is, some of the most basic, essential things for us are all tacit. I mean, in fact, my joke is, if anybody ever asks you, write 10 reasons why you like me, refuse. Say, it's your essential you-ness that I like. And then you can never get into problem. Because anything you write can be falsified. I like you because of hair. Oh, that means when I lose hair, you won't like me. I like you because of your knowledge. Oh, that means if I get dementia, you won't like me. We want to believe that people love us for our essential you-ness, which is like a cry for, I don't want language. Right? Most important things in life, we actually romanticize tacit everything. Okay, but imagine trying to give pairwise comparisons. I mean, actually, apparently, the Facebook, the original idea for Facebook was pairwise comparisons. Remember the one basically who is heart versus heart versus heart apparently. But mostly, you still depend on giving some linguistic descriptions of the types of people you like. And then, of course, when you date, you say, that's not what I meant, seriously. I didn't want to say what I really wanted to say because A, I don't know, or B, they would throw me out of the platform. Either which way, I put you something to get to see. So the interesting point is we try to put words for tacit knowledge things. Very weird. Okay. And the real problems in the world are a weird mix of explicit and tacit knowledge tasks. Like, so for example, robotics, basically they talk about task planning and motion planning. Task planning and manipulation, path planning, etc. The path planning, manipulation planning tends to be a lot more tacit knowledge. Task planning is more like PDL planning. And you have to combine both. Okay, so if you're asking yourself where should PDL be used, where should RL sort of stuff be used, remember this one thing that you should ask yourself. It's like asking the question, where should Python be used and where should assembly language be used? It's a silly question to ask. You use Python when you can, and if you can't, then you use assembly language, because that's always like you catch you there. There's nothing that a computer can execute that cannot be written in assembly language. But there are, and every Python program corresponds to a particular assembly language program. But not every assembly language program corresponds to a Python program. You know this? Right? So every linguistic reward specification corresponds to some arbitrary extensional representation of it might correspond to certain, pairwise comparisons. But pairwise comparisons can't necessarily be represented in a compact linguistic representation. Right? So when you can do the first one, do it that way. Right? One thing before we take a break, basically is, since I talked about planning and RL, one interesting thing is, planning is deterministic, we agreed. RL, so MDPs are stochastic, planning is deterministic. Typically, planning tends to be deterministic. You can do stochastic planning, we'll talk about it too, if you exam extra semester too. But, we can talk about that too. But the more important thing is, RL also allowed generic rewards, right? So planning was like, it's all or nothing. At least some of you have heard of things like trajectory constraints, but I didn't really talk about it here. So in general, it's like get all these goals true by the end. So the question then is, what will it look like if I generalize that part out? And basically, there is this idea called oversubscription or partial satisfaction in planning, which is basically starting from the planning end and making the goal specification be a bit more flexible. You don't have to achieve all the goals. What you wind up saying is each goal as a utility. So you get the goal, you get that much utility. And if you get 5 of the goals, then you get addition of all the utilities. Simplest model. But utilities can also have dependencies, right? For example, like right shoe, no value. Left shoe, no value. Both shoes, good value. Right? And 0 cars is worse than 1 car. Right? But 2 cars is not double as good as 1 car. And 15,000 cars is a nuisance. Right? So there are all sorts of the additive utility doesn't really always work, but act as if it works in the simplest case. Okay. So in this particular case, apparently I'm going from place to place, and so if I go to San Diego, I get to see the zoo, and then apparently I get 50 points. And if I go to Disneyland, I have some fun, I'll get 100 points. And if I go to apparently AAA San Jose, I don't know when this was, but I guess 2004, AAA was in San Jose, you'll get 300 points. Okay, and similarly, the cost of going, each of these things have costs. This is the path. So in general planning, actions can have costs. Goals can have utilities. And then the objective of planning, so up until now, in PAL planning, there was no notion of talking about optimality. Optimality was just like things like the least number of actions. And when you have time, you can say least number of actions. If you have cost of actions, then least number of, the total cost of the actions has to be minimized while the make span is, also minimized. So that was the multi-objective. This one is a lot more of the MDP kind of a thing, where basically it's oversubscription planning, which basically says to get to a goal, you have to spend money because you have to do actions, that's cost. And imagine, actually this is not always true, but act as if the units of the cost and utility is the same. That's another huge simplification. It's all dollar value. Everything important is converted to dollar value. Right? Imagine. Right? So then the interesting thing would be, if you want to get all the utilities, then I have to do a circuitous path that will also have a high cost. It's not obvious that the total utility minus the total cost will be positive. It could be negative. Do you understand what I'm saying? So the interesting thing becomes, here are all the goals I can collect. Here are all the costs I have about reaching, making plans that will achieve those goals at different points. What's my optimal plan? So that sort of tells you which goals should you first focus on and then convert it into the classical planning problem. But that's wrong. That's basically like doing temporal planning by doing classical planning and removing the RLs. What you really have to do in the most general case, it's an MDP. You have to actually write this as a deterministic MDP and ask for the optimal policy. Do you understand what I'm saying? And so here is a classic direct connection. I mean, obviously, normal planning also is MDP, except it's a simple way to convert. The goal-bearing states will have, +1 and their terminal, and non-goal-bearing states will basically have like just the cost of the actions. That's it. Now the interesting thing is, how would you convert this into MDP? Obviously, the dynamics are the same, right? It's like basically there are actions from state to state. The question is reward. How do you convert it to a reward function? This is an example of how converting an obvious thing into a reward function can actually be tricky. The most obvious thing is that any state where you have visited Disneyland, right? I mean, have visited Disneyland. Any state you have visited Disneyland will have 50 units. And reward, because the word utility here actually is just becomes reward, immediate reward. Once you get that, you get this immediate reward. Do you understand this, right? So any state, this will give you 100, this will get you 300, etc. So then I can just say, just like classical planning, I can say every state of the world where you have reached Disneyland, you get this much money. And you reach this other state, you reach this much money. And then the transitions will have cost. Is that fine?
I'm just like doing an assumption, but potentially if you've already been to Disneyland and then you go a second time, you shouldn't get the
Very smart. There's a huge problem here. You can keep going back into the state many, many times and keep getting, because it's not, you may feel the surfeit of Disneyland, but your machine doesn't. It's just numbers for it. Add. Keep going back, add. These are what are called quote unquote reward hacking nonsense. Reward hacking is nothing but misspecified reward to begin with. So you specify reward like this, and you think people will understand that they're not supposed to go to, good people will understand they're not supposed to go to Disneyland too many times. But who are you talking about? This is a machine. It's just going to do what you said in the reward. And reward hacking is actually taking the specification of reward you gave at face value. No more, no less. It's not doing anything other than taking what you said in the face value. And that's become called reward hacking. So it's like this business of will, that is, do what I mean, not what I say. Right? But what I mean is huge amount of common sense knowledge. That's not there in what I gave. Other people who share my common sense will decode my reward specification that way. If the machine doesn't, is it reward hacking, or is it just doesn't have the common sense? In the Seinfeld episode, one of my favorite Seinfeld episodes, which unfortunately is not a particularly family-friendly one, George Costanza basically winds up having sex with this woman in the office, and then he gets caught. And then his thing is that wrong? Really, if only somebody told me when they took me in that this kind of stuff is frowned upon, I wouldn't have done it. Is that reward hacking or not? I mean, basically nobody tells you when they're taking you to the job that one part of being in the job is not blowing up the building. The other part is not having sex with everybody in the office, during the office hours on your desk. They don't say it because they assume this is implicitly understood. Right? But implicitly understood for people with some common cultural common sense. And you can hack it. You can act as if I'm not from here. I don't know. I mean, in my place, this is normal. You understand what I'm saying? So reward hacking is actually taking what you're saying at its face value. So then the problem becomes specifying. Actually, I should also write this down somewhere. There's so many things and I forget myself. What happened is doing exactly what you said. No more, no less. And you are saying, do what I say with common sense. What the heck is common sense? I don't know. If it's not important, why don't you tell me what common sense is? You understand what I'm saying? So the interesting question in this case is, the more obvious thing is you could have said this to people and they would have understood it. But your MDP won't understand it. And so, given the specification, the natural right thing for it to do is to go back to the highest reward state and keep coming out, going in, coming out, going in, coming out, going in, and keep getting lots and lots of reward. That's exactly what you said, supposedly. How do you stop it?
It's kind of like turning the non-Markovian into Markovian, where like you have a state for when you've seen something once, and then from there you now can only access states where you've seen it like since then, and those.
Basically in the right direction. And notice suddenly non-Markovian reward. This is a non-Markovian reward. Right? So you have to see how many times have you been here. Now the simplest way, the way you are doing it, like you have to keep a count on each of the goals. But the advantage of your approach is basically that means if you have the number of times you have reached this goal, the number of times that should be your state variable. And it can have integer values. Maybe it can be true false values. I mean, haven't seen it before versus not seen, has seen before. So if you give one for each of the goal states, then there are n such goal states, n goals, then you have expanded, you multiplied the state space by 2 power n, which is okay. At least it will do what you are expecting. The reason I'm saying this is it's not obvious how to convert what you have in mind into what an alien will understand. In this case, it's an alien, basically doesn't have your common sense. The reason you expect people to do the right thing is because we have common sense. And common sense, the more important part of common sense is common. And it's very endemic stuff. There is no quote-unquote common sense that transcends all cultures. Some things like, you shouldn't randomly kill people on Fifth Avenue in New York is probably everywhere. But certain other things, such as you should never wear shorts outside. Like, you wear shorts in India. I mean, if I wear shorts in India, they just think, poor guy, he's basically, all these studies and he just wears shorts. Here, nobody cares. It's a completely different culture, cultural common sense. Right? I mean, we have to talk about what common sense do you mean? What values do you mean? By the way, this other word that people use, Stuart Russell is very much into this. What actually is his life's work? Right? And the point is, how do I say it such that they will never do anything wrong? And of course, in some cases, you can actually prove that what you said is exactly what you want done. This is one of the cases where this gentleman gave you an example. Turns out it's actually inefficient. A much simpler way is just have a single variable called done collecting. And the done collecting is false before, and it becomes true at some point of time. And once it becomes true, that's when you collect the rewards. So it's not done collecting, so done traveling. So after doing the traveling, the done traveling part, then you just collect all the rewards at one time. And so in some sense, the entire state space is just doubled. Everything without being done versus with done. And you only have non-zero rewards in the done part. It's all zero rewards in the non-done part. And if you think about it, that actually gets you all, for this problem, you can completely represent it correctly. The kind of versions you are talking about can allow all sorts of interesting other kinds of rewards too, such as certain goals can be collected up to 3 times and other goals cannot be collected more than once, etc. right? But the interesting thing is, notice how tricky it was just to convert what you directly understood commonsensically, that, like their goals, and I can't achieve everything, and so everything that I actually achieve, the cost is subtracted from the utility, and that's the net benefit. But to get MDP to do it right, you need to give it in the assembly language. That's correct. That's alien for you. Right? Now, so how many of you know this whole Midas, King Midas and his golden touch? What the heck is he complaining about? This is basically reward misspecification. Right? I mean, like, first of all, no human, if a human, non-alien human came and said, I want to give you whatever you want and tell me what you want, first of all, you'll probably be stupid to ask them, make everything I touch be good. Right? Because you know that if you have a reasonable mental model of humans, you know that none of them are alchemists. Right? But secondly, if they were such people, they would also have a common sense of not, making his kid becomes gold, kid become gold, which is the problem of Midas. He's talking to the superhuman thing, which clearly doesn't have the same common sense as he has, and he just tells it that, make sure that everything attached becomes good, and he does it. There is a much nicer version of that, which I actually like better. So this guy, from India has essentially done like a large amount of prayers to the god Brahma, who is one of the big gods in India, who apparently created the whole world. And Brahma basically is also an easy enough guy to get impressed if people are praying to him. So he comes and says, what do you want? And this guy says, I have first some couple of questions and then I'll tell you what I want. And he says, what are the questions? He says, is it true that everything in your world is hugely bigger than in our world? He says, yes. So is it true that something like 1 rupee in your world would be gazillion trillion rupees in my world? He says, yes. Is it true that 1 gram of gold in your world will be gazillion billion tons of gold in my world? He says, yes. And he says, I just want 1 gram of gold and 1 rupee from your world. And he pats himself on the back. And the Brahma says, I'll be back in a minute. What made you think that when the cultures are so different, time suddenly becomes the same time? Right? The reason you could laugh at it is because you have mental models. You won't be King Midas. He's a bozo. You won't be. Right? I mean, if you have, first of all, gods are not real. And secondly, if you're talking to aliens, you don't assume that they have the same knowledge. If you're talking to Martians, you won't assume, would you like Coke or Pepsi? Everybody likes Coke or something. What nonsense. They don't like anything. Right? So common sense doesn't exist unless the word common actually exists. You see what I'm saying? So reward hacking essentially is you are always specifying what you want in an incomplete form. And there's a whole bunch of hidden constraints that you don't specify. And people are supposed to supply the completion of the reward. The indirect constraints, we do that, right? Basically. Like if you have to go to school fast, then you realize that you're supposed to go to school fast without weighing down people on delay. I didn't say that. Is that bad? Am I supposed not to do it? But I didn't say it because we assume this is our common sense. But when common sense doesn't exist with necessarily machines. However, with LLMs, to some extent, one of the good things for LLMs is they actually captured human common sense. In fact, they're not the best, but they have done a better job of capturing human common sense than pretty much anything else, Gary Marcus notwithstanding. There is no other way. Right? Our common sense is the complete, the union of all the amount of writing we put on the internet doesn't subsume our common sense. I don't know what else subsumes our common sense in a better way. So actually you can use LLMs to complete the reward specification. Sometimes. Right? And they'll basically copy what humans might have done in completing the reward specification. Okay? So anyway, so that is the thing about, net benefit planning and partial satisfaction planning. And there's like a whole bunch of papers on this that some of us, we also wrote. I mean, I'll send you some links, but it's interesting. It's a middle ground between PDL planning and MBP. It's deterministic MBP, but with more interesting reward functions, right? So you can actually have all sorts of interesting. The plan complexity doesn't worsen too much, but it's like one of the things that I like to say is which is better, oversubscription planning. That is, you have a whole bunch of goals, and you get to decide how many goals to attempt for, and how much, what's the best plan. Versus, I tell you upfront all your goals, and you must achieve all these goals. Which is better?
First one.
Which one?
The oversubscription one.
Better in what sense?
I mean, you can hit how many other goals do you want to hit, which could arguably zero.
So, but do you guys realize that not doing anything is all of a sudden a plan for oversubscription planning?
Yeah.
And if you don't do anything, no cost, no benefit. It's exactly the opposite of no pain, no gain. Right? So you don't do anything, you can't get cost, of course you can't get reward too, so it's like 0 minus 0, still 0. You could be doing negative, man, with these kind of things, right? You did better. Undergraduate versus graduate education is, one of them is partial satisfaction planning, one is full achievement plan. Graduate education is basically do the right thing. I'll tell you lots of papers, I'll tell you all this stuff. You can give up on the rest of your life and only spend time on my class, which is the optimal policy as far as I'm concerned. But I'm sure you will be like alone after the class is over. And so you can also do a valid plan of, I listen to Rao, laugh at his jokes, and go home and come back again. And he keeps saying there's this exam that's like clearly using my common sense and unexpected hanging. It's not going to happen. There are only 3 classes left. What is this going to happen? This is not going to be the exam. This is what you might think. I'm not saying it's going to be the exam. Right? So, the problem with graduate education is you can achieve a whole bunch, or you can just take it easy. In undergrad education, we tell you, this week, this is the assignment. This next hour, this is the quiz. This other day, you have to do these 2 assignments. This another Friday, you have to talk to 3 people and interview them. You hated undergraduate education. But really, graduate education is harder on you. Because you have to use your brain. We use our brain to set your goals that you should be able to achieve, so that we know approximately what makes a okay undergrad. And we said you must do all these things to be calling yourself an undergrad. To be a grad student, I mean, many of undergrads know this. Are there undergrads here? You know that grad students basically, this is a secret that I'm sure grad students won't want me to tell you, but there is a rule in graduate study, in our school as well as many schools, that if GPA falls below 3.0, which is a B average, then you will be on probation. You put a rule, then students will then come to me and say, do the needful. If you give me a B, I'll fall below 3, and are you going to just let this happen? I'm just going to die. Now I will be thrown out of the program. So the rule, which was you should at least get a B, has gotten into, in the normal way, most grad classes mostly just have B's and A's. This is well known. And here you are taking 310, where it is D minus, D plus, D plus plus, C minus, C plus plus, etc. And you kill yourself there. But in the grad classes, people are just laughing all the way to that. All of you are thinking you are going to laugh all the way to that. Because how bad can Rao be? Does he give a B or a C? And not a C, because people will be sad with C, etc. Right? In general, this is true. This is what basically happens in the grad thing. Right? So so the point is that in undergrad it looks like we made your life harder to some extent. Right? Because we told you exactly what you have to do, but we used our brain to decide what you should be doing to call yourself an undergrad. I'm teaching this grad class because I don't have to use that part of my brain. I don't know whether I'm using any part of my brain, but that part of my brain I don't have to use because I tell you all these things. This is the huge rope. You can use it to hang yourself or use it to pull yourself up. That's what grad course is. That's what life, by the way, is. You see what I'm saying? Life is an oversubscription planning. Life is also an MVP, life is all this stuff, but definitely partial satisfaction planning. It's like there's a zillion things you want to achieve, but there's no time for all of them. And it'd be simpler to, especially given the paradox of choice. You know, guys, do you know this this donkey called Buridan? It's called Buridan's donkey. Buridan's donkey. Who knows? Okay, what is Buridan's donkey?
A donkey is set between two bales of hay and it will just stand there and not know which bale it to go to its own regular start.
Standing between two equidistant bales of hay, the donkey starves to death because it can't make up its mind. That's what I'm saying. So, given the paradox of choice and the natural laziness, people are likely to kind of take highly suboptimal plans. The notion of invalidity of a plan is much less. There is no such thing as invalid grad study. You know, again, I'll tell you another of the, dark dirty secrets, right? PhD thesis value goes between 0 to plus infinity. Actually, not minus infinity, hopefully. Plus infinity, 0 to plus infinity. And you can actually get a PhD with a zero value PhD. People are doing it every year. Because eventually, after 5 years, people can't stand you. And you know, there would be a few things that you're supposed to complete, and then the rest will basically, like unless they, especially in a culture where people, all sorts of people can have stuff like guns, you're not going to be taking, 5 years, I'm going to take a stand, you're not going to pass the defense. That's not going to happen. What instead happens is you get a degree, but people know whether you're good or not based on your track record. That's like oversubscription planning. Every plan is a plan. Empty plan is also a plan. Empty plan was not a plan for Bloxworld. You understand what I'm saying? Because you can't just say empty plan, what's the value? It's not even a plan. It has no value. But empty plan is a plan for oversubscription planning. It has zero net benefit. The question is this the optimum? So it turns out that the search is now harder. In some sense, partial satisfaction of goals is harder. Just like partial visibility is harder than full visibility or no visibility. Partial observability is harder than full visibility or no visibility. Computationally speaking. Partial satisfaction is harder than you must satisfy all the goals, and I tell you which goals you have to satisfy. Because I decided what you should do. And you wish I told you all those things. I mean, instead of saying this navigating thing about read this, read that, etc. Just tell us which ones are going to count towards the grade. But life doesn't go that way. And the closest in academia to life is grad school. Right? What you get out of the course is what you put into it. What you get out of the oversubscription plan is what you put into it, to some extent. Of course, you can also get negative values, right? You can do a whole bunch of cost and still ultimately didn't learn much. And you could have been enjoying life by watching movies during the semester. That's your brain deciding your deliberative action. Yes?
So wouldn't oversubscription planning be like a factorial to the power sort of?
That is the interesting thing. So the point is that in terms of the complexity, it's the same. Complexity is the same. It's just the way you could, actually there's a whole entire work on this. I mean, we are at some point of time, like 20 years back, we did a whole bunch of work on this. So these are all our, Archiplan. Archiplan, by the way, is an IP-based planning framework. It's a programming-based planning framework. ALTAR PS is some sort of a graph plan heuristic-based planning PS framework. SAPA is also, SAPA, partial satisfaction planning is another version based on the same algorithms, which basically have been changed to, and this is of course the MVP modeling. This stuff is what I was just telling you about how to model it. Okay, so that's about oversubscription time. And I just brought it up because it's a continuum. It's not planning here, MVP here, that one can't be. There are things that are in between. And it's the trade-offs that you want to understand. Trade-offs of modeling, trade-offs of computation, trade-offs between learning versus inference, doing inference by lazy methods, for example. Okay, so, and then I'll come here right after our little break, and then I'll talk also about world models. Yeah, this is the simulator stuff I told you already. This planning versus RL. And this one last time I showed you, but this is the thing. RL is just a lazy way to do planning if you know the model. And so, if you actually know the model and the model can be written in the PDL or whatever, some language, you would find that those algorithms do way better. Right? And that's basically what happened in that competition. But people just do RL, do learning when actually it's just a inference problem. Okay, so I will take a 15-minute break and we'll come back, I guess, for 15 minutes. Okay, I'll skip this. I'll get back to this in a minute, but later. So again, this is the background, so I want to bring it up once and for all. World models, essentially, as I said, I hope this is like repetitive for you, but it's a fancy name for a transition model. Specifically, a world model answers the question: if you are in state S1 and do an action A1, what will happen? Right? And you can answer this mentally. You can answer this by calling the simulator. Actually, I should write this down. That's probably a good thing to do. You can answer this mentally or by calling a simulator or by doing it in the world. Yeah, so that's basically the thing. Okay, now most of the time when people are talking about world models these days, they are talking about learning the world model. And the question, of course, is what sort of the model are they learning? Are they learning PDL-like world models? Are they learning more pixel-to-pixel transforming world models? Much of the, and in fact, the name world model basically has gotten totally messed up. So there's a long tweet that I have that I'll show you in a minute, but I'm discussing that, but you can also read that. Essentially, people confuse lots and lots of different things in terms of world model, but the best way to think about it is essentially it's a transition function that you're trying to either be given or learning. Okay. In planning, we assume the world model is given as part of the problem specification, like the PDL model, but you can of course learn the PDL model. One way of learning the PDL model is extracting it from LLMs. It's a weird thing. It didn't exist before, but now you can. Right? Essentially, one of the other slides that I keep mentioning, I will bring it today, is LLMs opened up a different way of quote-unquote learning. It was not there in the supervised learning, unsupervised learning. It is learning by asking, essentially. Learning by asking an unreliable source, essentially. Right? And that's just a very different way of learning. And basically, the theory of it is very questionable because the source unreliability hasn't been well characterized. Okay? Anyway, so you can of course learn the PDL model by extracting it from LLMs. In RL, the agent can learn the word model on the way to computing the policy in the real RL. Do you see what I'm saying? And one of the interesting things that can happen is, imagine an RL agent has an internal simulator that it's calling, and as part of calling the simulator, it can actually compute the translation function itself. So then it sort of took into its mind what is available outside. It's still not the real world, but it's like you keep calling the calculator for saying 4 plus 3, and it seems to be always giving 7. After a while, you might realize 4 plus 3 seems to be 7. So you don't call the calculator. So you learn the translation model mentally. But you also had it in the simulator, which is your calculator. Do you understand the distinction that I made? Okay, so basically RL, always learns, any model-based RL kind of learns model. And one of the interesting questions is, what does model-based RL do when there is a simulator? One of the interesting questions, I probably should write it here, is even when there is a simulator, the RL agent might learn its own internal transition model. Think of it as materializing. How many of you know the notion of materialization in databases? So you have a database, you have the notion of view of a database. A view essentially is a query. So even though that entire database exists, you only get certain queries to be asked. Like for example, my question basically is, I like to, I don't know, maybe I'll use this example here, but if not, then it will be interesting to you. I somehow am one of these strange people who likes to read books that have between 343 to 347 pages. Some people like Western, some people like classics. I like books with 343 to 347 pages. That's my thing. You don't get to question my government. Right? Now, Amazon really knows what books have how many pages. But can I search for it? You can ask for, like, give me books by X. You can ask for, give me books by, books that have this word. You can't ask for, give me books that have 347 pages. Why? Because the view restricts you. This is how you get security in databases. Right? In fact, the university knows your social security number. I can't just ask it. Right? Because the queries I have don't give me the social security number. Right? But if I do there are two issues in there. One is, if I do really want to get all the books with 347 pages, is there a way I can do it?
Start building your own data set out of searches.
So basically, what you can do is you can essentially okay, give me some books written by like some Westerns, and I'll give you a whole bunch of books. So put these books and then check which of them. When it gives the record, it will have the page numbers. Unlike the search secret number, which actually never is shown. When it gives the books, it shows the number of pages available. So now you know the pages. So you can which ones are 341 this thing. And then once you give the books, it gives some more names of the books and some more other words. You search recursively. So this is what is called a recursive information gathering lab. A recursive information gathering lab. And you ask Amazon multiple times with all the things that you can think of, it will keep giving answers unless it throttles you. And then you can ask, John put it very well, this way you are materializing Amazon's database. You have your own little copy. Right? So you can think of when there is a simulator or even a world, and the LLM and the agent, RL agent is computing its transition function on the way to computing the optimal policy. What it is doing is ultimately some materialized version of the true world or the true simulator or the true PDL. Did I making any sense at all? I mean, by the way, last two classes, if they made sense to you, you're getting a lot out of this. If it doesn't make any sense to you, sorry. It's because it's somewhat more abstract. But it actually helps in terms of understanding what this paper is studying. Right? So, so think of, even when there is a simulator, essentially you are learning what the simulator will say. And these are your statistics about what the simulator will say before calling the simulator. And you can think of world and simulator to be pretty much the same. It's just that in the simulator, if you die, you don't die. In the world, if you die, you really die. Right? And then basically, RL always computes a model for itself. Right? The question, of course, is at what level of abstraction is this model? So the issue would be this transition function in terms of states. The question, of course, is the notions of abstraction that we talked about earlier on, they all matter here too. So the question is, what sort of abstract level? Is it like pixel-based state to pixel-based state, or is it a pixel-based state with state features? And you think in terms of state features, and the state features either are making sense to you, or the state features are essentially some internal nodes in some big network. Okay, so the abstractions matter. And so the interesting, so this, you can look at this, I'll send you the link, but essentially the things the things that matter is the resolution of the states, that is how much specific information do you have. So if you take a picture of the state, if it is a physical state, you take a picture of the state, right? You get all the pixels. Everything you do is subsumed by the pixels. So if you see a block there, that means it's a subset of things that people would call a block. Okay. Of course, there can be non-physical scenarios where actually, a lot of work basically would be like mental scenarios. So that there actually symbols cannot be avoided like at all. So for example, if you're talking about, I'm putting money into my account, this much money, and then I'm withdrawing this much money from my account, how do you write this as a pixels? This is basically the reason why dogs don't have banks. Right? They don't have banks because they don't have symbols. Right? So to some extent, those will be higher levels. So resolution versus abstraction. And then I also mentioned abstraction and disjunction are well connected, multiple times. And role of language in symbolic abstractions. I kind of mentioned this multiple times. In general, if we have abstractions at all, we typically, especially the civilization enabling abstractions, they are all linguistic. Again, think about somebody else coming back and saying, but what about 37th move? And remember what I was talking about 37th move. 37th move essentially is in the vocabulary that we have more or less described for the actual search process. Okay. Then internal abstractions and alignment problem is important, because if in fact the machine learns abstractions from the pixels, like the Java style abstractions, that might improve its efficiency. It may still not actually know whether those abstractions will correspond to the kind of abstractions that you have. So alignment problem, as bad as what people say LLMs are hard to align, it's nothing compared to aligning to aliens. Right? Basically. And so the alien, basically anything that learns from pixels, its own internal abstractions is going to be extremely hard to make sense of. Okay. And then by now you should understand that verifiers and simulators and world models are basically connected to world models. And there's world itself. World is its own best model. Right? And then everything is an approximation of what the world does. And the approximations can have different syntactic properties. such as are they declarative, are they procedural, are they black box, etc. And if you understood what I discussed today, that sort of makes lots and lots of things very much more sane. So for example, there was one of the earliest papers, I believe React, which was doing quote unquote planning stuff with LLMs. They write the whole thing, and actually you should read the React. Maybe I should make you read the React. And we should also read our paper, debugging it. And that also got published, but obviously the React paper got lots and lots of editions. I'm not going to write anything. But the point basically is that they use, it's like a poster child of everything I was telling you earlier. That is, instead of saying I'm doing a star search, say I'm using like PALM DBs in partially observable worlds, partially observable worlds, except there's single agent and it's fully observable, etc. So they construct this whole React system as if it is interacting with the real world in an RL fashion. And their world is a PDL model. If you read the appendix, they're using a PDL model to simulate their world. If you already have the PDL model, why don't you use it? What's the advantage of converting it into something else just so that you can say that you're using, either learning the model or basically doing RL. And what you have to do is planning, essentially. Okay, this happens all the time. And then the other thing that I made a big deal about in this class is learning from your experience is very different from learning from other people's experience. If you learn from your experience, you will feel the reward like I did. So you know what to do. Learning from other people's experience, you need to do IR, which is essentially kind of giving them a reward function, even though they didn't tell you what the reward function is. So under that reward function, what they're doing would be rational. And if you do that, then you can generalize it. So in general, learning from other people's other people's experience, typically you can either do imitation, just do what they did, which does have a lot more generalization issues. And if you learn the reward, then you have better generalization. Shouldn't be surprised. But it's a harder problem to learn the reward. It's easier to just copy, right? And then the other thing that I also mentioned here, but you can look at it, is so this issue of React, basically something like React doesn't say it, but there's a whole entire work on world models right now that basically starts with synthetic games that people have written, and they learn the world model for it. What's the advantage? What?
There isn't one.
You have to think about it. So the point is that it's like a huge number of people are doing it. I mean, it's not that if my life depended on it, I can make some arguments. For example, you are essentially materializing the code into your head. But in the case of Amazon, I wouldn't do the materialization of Amazon database if there is a way of asking Amazon, what are your 341 page books? If I can get it, why would I do it? So you would only do the simulators model you would learn separately because simulator code is not accessible to you. But is that a reasonable assumption in this day and age where every piece of code on GitHub has become part of the training data? You see what I'm saying? And in fact, this becomes an interesting issue. Like a whole bunch of people, there's the Voyager system, for example, which does like Minecraft kind of things, and then they will say that they're using RL. First of all, again, that's another thing, we should read these papers and actually look at this, with this perspective, read it and try to make sense. Then you learn something, okay? So one of the things, of course, is, Minecraft models are well known because there's enough data about the Minecraft. So you can ask LLM to just give you pieces of code for the actions and skills and everything, which is exactly what you want. Okay. So basically, I still think that you can understand what's going on in terms of world models with this picture, which is basically what you see in the intro to AI. But Jan likes this picture. Really, there's no difference, honestly. And so one time I actually said this, that it's the background Stuart, because Stuart being Stuart Russell. And Stuart Russell had the bad background, and Jan had the brain as the background, and you cannot go wrong with the brain as the background. And then Jan got back to me and said, well, the thing on the left is not differentiable, the thing on the right is differentiable. First of all, it's not right. It turns out that nobody ever said this thing cannot be differentiated. It depends on what representation you use. Differentiability is a vehicle. You have to decide what you want to do and what conveyance you want to use. Right? And then, but again, most people actually look at this and think, the entire stuff about world models right now, people who hype it up actually don't understand this like at all. If you understand this, you will understand what's the difference, as against this thing just came out of nowhere. By the way, one other interesting question is, there is the current difference between Jan and Yoshua is the following. Yoshua says, you should train models to learn without goals. Because the goals might be set by evil people and they'll wind up learning certain kind of bad things. I should train models to learn without goals. That's just one model. You just explore and compute a transition model and a reward model for the entire world. And you're off policy all the time. That's just that. Okay? Anyway, so one other thing here is, anyway, so you can look at this. So the other thing that I want to mention, again I mentioned in the class, but I want to repeat it again, is if you do learn world model, how are you going to use it? You have to ask yourself, right? Because everybody is saying we are using world models. Okay? The most obvious way to use world models is the classical way, which is if you had a PDL model, you will have planner to basically convert that into planning out your way. If you have SAT model, you get a SAT solver to convert it into assignments. If you have CSP model, you convert it into like a CSP assignment with the solvers. But better or worse, LLMs opened a new world, where whether you like it or not, they've been trained on everything that's available on it. So it opens up a different way of using the world model knowledge, which is basically let the LLM guess and you check using either your simulator or your verifier or your world model. You see what I'm saying? So LLM modulo with learned world models are given verifiers, are built simulators, is a competitive method compared to just using the world models and using classical techniques. Because you have to have some other techniques for actually converting the world models into policies. How are you going to do it? Okay? So that's one of the other things that, and that's basically the talk that I was giving at Georgia Tech. And then, so if you're using world models, and I'll take 5 more minutes and then you can go home. If you're using world models, verifiers, and simulators and LLMs, in the test time, you just do LLM module. Essentially, you guess and you have these things checked whether the guess is correct. More correct versus less correct, depending on how good your model is. Right? So previously, I just made it, the question about these verifiers is where are the verifiers coming from? Verifiers are sometimes available for, in fact, for most of the scenarios where LLMs are working well, we have verifiers. Math has verifiers. Programs have verifiers. And planning has verifiers. But if you wind up learning verifiers for other domains that don't have verifiers, you could then use that in the context of the generate test. And it will be a better generate test. In the test time. Now, if you have the verifiers, one of the other things you get to do, interestingly, in the case of LLMs, is you can use the verifiers and your guessing ability to convert it into a humongous amount of additional data. Problem, solution, problem, solution. And if you give lots and lots of problems and lots of solutions, and you fine-tune the model such that it will actually produce those kinds of completions. When it sees these kinds of prompts, it produces these kinds of completions. It will become a better generator. Normally, this is what has been called fine-tuning. In the original way in LLMs, fine-tuning would be people will make extra problems of interest to them and their solutions and collect like 500 or 6,000 of them and give it to LLM to fine-tune it. Right? Now, with the verifier, you no longer dependent on the humans. If it's a formal problem, you have a verifier, you can generate unlimited number of problems, basically solve them using LLM modular. Right? I mean, there are slight differentials, but think about it that way. And you can get large number of problems and their verified solutions. And then you fine-tune the LLM. That's basically what has been the reasoning models, yes.
If there's like, so let's assume that like this generate test is not perfect. Like for some reason you're not able to solve every problem. Then this post-training thing should just exaggerate that bias, right? Because then whatever. Like,
no, actually, so even if in fact test time is so test time has guarantees because the verifiers are, if their verifiers are complete, let's take the other side. If the verifiers are complete, test time has guarantees. But post-training still doesn't have guarantees. It is just that you try to produce things like the ones that you have seen. And so you still, in fact, if you want guarantees, you essentially still want to put the verifiers. And your question is slightly different, which is if to begin with the verifiers don't have guarantees to begin with. They're better than it's any verification. So it's better than just the simple guess of the LLM, but they are like faulty verifiers. So they have like false positives, false negatives. The question is, will that get exaggerated? Of course, it's getting exaggerated even when it's fully correct. So that actually is the reason to ask, why can't you just use LLM as the judge itself? Why care about PDL-based verification of plans or lean-based verification of math tools? Why not just have a GPT-4? Is your proof correct? Right? And nobody does that. And that tells you that there is a signal that is coming from the verifier, which is being compiled painstakingly into the generator. Now, one of the issues is it's kind of, so this is a picture that I made from the old fine-tuning. It's very much true for the new fine-tuning too. The difference between the old and new fine-tuning, honestly, is especially if you generate your own data, like if you don't depend on the humans to generate the data, the only difference is this thing of intermediate tokens, which we'll get into at some point in time. Okay, but really, did I show this slide at any time? Okay, so basically you know this. So in the sense that instead of just calling a planner to solve the problem, you call the planner to solve 1 million problems and fine-tune the LLM. The only difference between this and LLM modular is instead of calling a planner, you have LLM as a generator and you have a plan verifier. And then you fine-tune the model. The question ultimately becomes for all of these things, how well has it generalized out of the distribution on which it's been trained? The answer to that, none of us know. Okay? But it's basically what we are currently doing. So this, again, is one of the things that after today's class you can understand this. Maybe you can explain. With enough deductive closure data and GPUs, any reasoning can be converted into approximate retrieval so LLMs can fake it. Can you explain what I might be meaning? I'm not necessarily saying it's correct or wrong, but tell me what I might be meaning. Somebody.
If you have enough examples of something, then you can kind of search to find something.
So basically the deductive closure data is if I have the plan, input and the goal, and I have the verifier, then all the correct plans are in the deductive closure of that combination. Right? And if you generate enough of the correct plans, solutions of the correct plans, and you fine-tune that onto the LLM, then essentially reasoning becomes some kind of a retrieval. It's not exact retrieval. The question, of course, is that's what the word approximate is. The $1 million, $1 trillion question is the approximate retrieval closer to just exact retrieval, or is it much closer to listening? It's on the spectrum, but we just don't know where it is right now. And I can give you examples on both, say in both ways. Right? Anyway, so, yeah, so that, and then let's just see one other thing. Yeah, so by the way, so since I kept saying this, I'll just show this and say that the ASGRL, but you probably forgot by now, that one was actually trying to combine essentially PDL style plans. So it takes the domain model, which is incorrect, which may be incomplete, and given the domain model, you can compute these things called landmarks, which basically say that all correct plans have to go through those landmarks. And then the RL will essentially find multiple multiple policies from going from one landmark to another landmark. And then you combine them to get the full policy. Right? But that's still actually a classical approach. This is actually 22 ICML, you know, by, that was still Keith's. By the way, that's the guy, you know, Lin Guan, who did that work. He got the Dean's Dissertation Award. I'll show one other slide because I mentioned it, and then I'll do the RL for LLMs next class because that's a very different problem. So I'll talk about LLMs for RL. So LLMs for RL, you can use LLMs to initialize the policy. So first of all, you understand LLMs and RL, they can be two different things. Is LLMs helping RL or RL is doing LLMs? Those are very different things. Okay. If you're using LLMs to help RL solvers so that they can do faster, then the usual thing is you can use LLMs to initialize the policy, you can initialize the reward, you can complete the reward, you know, the kind of common sense completions that I was talking about, LLMs can do it for you. You can guess the transition model, PDL models can be extracted from LLMs, right? And you can even get abstractions. In fact, one of the things is you can ask LLMs, you know, what's an abstract policy for doing these kinds of large problems, and it'll give you something. It's not guaranteed to be correct, but it's no worse off at the abstract level than it is at the concrete level. So they might as well ask both. And in general, this is the slide that I've been mentioning. Maybe I showed it to you once, but you know, please look at it more carefully. In the era of LLMs, the thing that changes essentially is in the old days, planning as well as RL had this hang up that we shouldn't ask people for any knowledge. You know, if you ask a domain modeler for PDL specification, that's like not AI. Right? These guys in OR don't care about it. They'll actually, that's why OR people actually have jobs, because they sell students to companies who then convert the company's problems into like IP formulations, and then they have a job. AI said, we'll just look at your problem and the AI system solves it. Right? And basically you're not supposed to ask anybody for anything. That was the general conceit. Because of which the logical thing to do is try to learn from pixel level, the lower and lower levels of knowledge, not lower and lower levels of abstraction. And their things are extremely inefficient. So inefficient that you can actually do any small hack and you will show improvement. It's not surprising that nobody has shown improvements on sorting algorithms. And when somebody showed in slight average case improvements on that matrix multiplication, that was big news. Whereas deep RL, every day you can show exponential improvement. Because it's such a lousily inefficient approach for doing things when there is knowledge about it. And the reason you are not taking the knowledge is because you have this hang up that we should ask people. LLMs change that whole thing. Because you don't ask people, you ask LLM. LLM is not people. But LLM is very much humanity as a whole in some weird way. And it has no impatience problems, it will give you answers for any questions you ask. So suddenly you can ask all these questions such as, you know, let's say, you can ask all these questions such as what's the policy like, what's the reward like. You can initialize a good policy. You can convert the human's preferences into a reasonable reward model. As I said, and all these things you can do with no guarantees. And so planning and RL both were trying to fall down the ladder of abstractions. LLMs just pushed everything up. On one hand, people say symbolic AI is dead. It's not. We're all doing symbolic there, essentially. Unless you're doing Java models, which is a different story. You're essentially doing symbolic models. You're writing language is symbolic. The fact that the inside it is neural network doesn't have any issue. That's not the point at all. You're not giving pixel input to the model. As I said, remember, if you're doing Atari games now, you would not do it at pixel level. You'll show the Atari game frame to a VLM, which will tell you like a symbol, like a language description, which you then feed it to the LLM, you're done. Much faster. Way faster. So basically, what happens is LLMs change this rather drastically. It makes it easy to get knowledge without making it look like we're inconveniencing any specific human. We are just stealing everything humans told each other. That's all. And in fact, one of the other interesting things is with the post-training, with the verifiers, you're also kind of able to convert the procedural knowledge, to improve the evaluation. So as long as you relax the requirement of the knowledge actually being correct. So then, as I kept saying, so basically you can ask all these things. So the million-dollar question is, how would you do planning if you have some doddering know-it-all ready to give you any kind of knowledge? How would you do RL when you have such data? And as soon as LLMs hit the scene, deep reinforcement learning mostly disappears. You can look at, I'm not making this up, you can look at the lyrics, etc. Because deep reinforcement learning for Atari games makes no sense anymore. It only makes sense for things for which there is actually no symbolic abstractions that anybody knows, such as manipulation tasks. Even there you can ask LLMs for some sort of linguistic information that improves the speed quite significantly. So it's like you can convert any planning and RL algorithm to do faster with LLMs guessing any piece of the overall puzzle. That's how LLMs help planning and RL. Basically, they convert everything to some extent this generators. They can generate so well that they can convert to generators. The correctness part will be the test part. So the other part, of course, is how does RL help LLMs? And the basic idea is, let's see, I understand, I said I'll do the next class, but I won't show this one. So basic idea in DeepSeek R1, we'll talk more about it later, is they don't necessarily use, if you look at DeepSeek R1, they don't necessarily use LLM modulo, but they use a version of it. They won't call it that, right? Because everybody has different names. What they do is, they will have the model generate 15 answers for a problem. The verifier checks which of the answers are correct. And this becomes the training data for that. The important thing is if you are generating 15 trajectories and one of them has to be, if all of them are wrong, there is no signal. Verifier says you are wrong all the time. The whole way RL will improve, basically the whole sparse reward problem. If all you get is 0 reward, then you are not learning anything. Once in a while you have to hit gold. So if you generate 15 trajectories and at least 1 or 2 of them are actually ending in the correct solution, that's enough. So what actually happens in DeepSeek R on all these problems is they will get the V3 in the case of DeepSeek R1 to a place where for a small sized planning or whatever problems, it has high enough top 15 accuracy. So top 15 accuracy of 93% means if you guess 15 times and one of them is correct, you get a point. So for example, my top 2 accuracy and true-false question is 100%. You understand what I'm saying? Right? So you have to understand that. Basically, it's a much weaker thing. So the top 15 accuracy is 93%. And then use that to generate the guesses. Have the verifiers check if the guesses are correct. And then use a form of RL called basically policy gradient, which I skipped, but I'll talk about it. Right? It's another RL policy implement out there to essentially change the parameters of the algorithm. This is what post-training is all about. And when you do this, then where you had 93% top 15 accuracy, you are converting it to 93% top 1 accuracy. When you did this, the neighboring problems for which you had very lousy top 15 accuracy, probably you have better accuracy now. So rinse and repeat. This is basically my best guess. Nobody has any better guesses. My best guess as to what is actually happening in the post-training reasoning models. Okay? I will stop here. Most likely when I come back next time, I'll actually change the topic to start talking about explainable AI, because that will be a different topic. And this stuff, as I said, this whole thing was discussed in those 2 lectures that I asked you to see long back. You can go back and look at them fully if you want. Okay? Thank you. Thanks for that. Just 1 second.